Okay, so applying what we just learned, let's look and see if we can find the complex zeros of some polynomials. X squared plus 1, if you want to set this equal to 0, you get x squared equals negative 1, and we know this has actually not one but two solutions, right? We have I and minus I. Okay, just like in the real case, if you want to take a square root, everything has two square roots, a positive square root and a negative square root. Okay, so and that means x minus I is a factor, and also x minus I is a factor, which is the same thing as x minus I times x plus I. Okay, so we can see that this, in fact, is x squared plus 1, because if you multiply things out, the ix terms cancel out, and then you just remember that minus I squared is positive 1. All right, now if we go to the example 3, let's look at this. This is a quadratic polynomial. We use a quadratic formula where a is 1, b is negative 2, and c is 3. If we do that, the quadratic formula says we take minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. This becomes 2 plus or minus the square root of negative 8 over 2. Okay, we can break this up as 2 over 2 plus or minus the square root of negative 8 over 2. This becomes 2 over 2 is 1, and this is going to be, we can rewrite this square root of negative 8 as the square root of 8 times the square root of negative 1. The square root of negative 1 is just going to be I, so this is the square root of 8 over 2 times I. And we can simplify this more by writing the square root of 8 is the square root of 4 times the square root of 2. So the square root of 4 is just 2. Okay, and that will cancel this 2 down here. So we get plus 1 plus or minus the square root of 2 times I. And we want to make sure that you don't put the I under the square root, because the I itself is a square root. So so the zeros are going to be 1 plus square root 2i and 1 minus square root 2i. And in fact, this will factor as x minus the quantity 1 plus square root 2i and x minus 1 minus square root 2i. Okay. And once again, if you multiply things out, you take your time, multiply things out, it turns out you get x squared minus 2x plus 3. So this is, I know this is a little strange, but the important thing is that in both of these examples we can factor this, the polynomial, as x minus some complex number times x minus another complex number. If we look at example 4, we have a third degree polynomial. It turns out that 6 is going to be a 0. We can use the rational zero theorem to find the potential rational zeros, and we get, in this case, it would be all the divisors of 24. And it turns out that 6 is one of them. And in fact, that would mean that x minus 6 is a factor. And either using long division or synthetic division, we'll see the quotient is x squared plus 4. I think right now, don't worry about this so far. You just convince yourself that this and this are the same polynomial. If you multiply things out, you'll see you get this. So we just need, okay, well, what are the zeros of, can we factor this? What are the zeros of x squared plus 4? If we set that equal to 0, we get x squared equals negative 4. So if we take, so x is going to be plus or minus the square root of negative 4, which is plus or minus the square root of 4 times the square root of negative 1, which is plus or minus 2i. Okay. So the zeros will be 6 and plus or minus 2i. And in fact, that f of x will factor as x minus 6 times x minus 2i, x plus 2i. Okay, you can check that if we multiply these two factors together, we get x squared plus 4. Okay. All right, now one thing you might want to see in these three examples is that if a complex number is a 0, we get another complex 0 just by changing the sign of the imaginary part. Here, the imaginary part is just I, and minus I is also a 0. Here, 2i is a 0, and minus 2i is also a 0. Here, we have 1 plus the square root of 2i is a 0, and 1 minus the square root of 2i is a 0. That is no accident, as we're going to see. We have a special name for this number. When we change the sign of the imaginary part, we call that the conjugate of a complex number. So we define the conjugate of a plus bi just to be a minus bi. And we denote it by just putting a bar on top of it. And some of you might have seen this already. So you're keeping the real part the same and changing the sign of the imaginary part. So the conjugate of 1 plus 2i will be 1 minus 2i. The conjugate of minus 6 minus 7i, that would be minus 6 plus 7i. Because in this case, b is negative 7. Here, there is no real part, or you could say this is the real part is 0, so this would be 0 plus 4i. So the conjugate of that would be negative 4i. Okay, 0 minus 4i. And then 12, this is 12 plus 0i. So this is just going to be 12 minus 0i, which is just 12. And we'll see that the conjugate of a real number is always itself.